Hello, this is Abby, and this is my organic engineering presentation on nylon. So, for the background of nylon, I'll just start with some general info. Nylon is actually referring to a group of synthetic polymers that are thermoplastics. And thermoplastics can be heated to their melting point, cooled, and reheated again without significant degradation, which is a useful attribute. And they're known as polyamides. They can just be referred to as PA as a short chemical designation. They're strong and lightweight, and because of the fiber characteristics, nylon dries quickly, resists dirt well, and does not weaken with exposure to chemicals or sweat. They're smooth, non-absorbent fibers, so they're really good for different fabrics and clothing and outdoor materials. They are melted by high temperatures, so 280 degrees Celsius for nylon 6,6, and the names have numerical suffixes to indicate the quantity of carbons between acid and amine groups, and we'll kind of get more into that. So two of the most common nylon compounds are nylon 6,6 and nylon 6. And if you'll notice, one has two digits and the other one is just one digit. So if there's a single digit, it means that it's a single monomer in combination with itself. But two digits indicates that there are multiple monomers. So nylon 6,6 is made up of hexamethylene diamine, 6 carbon atoms, and adipic acid. It has sunlight resistance, a high melting point, it holds color well, and it also has abrasion resistance. So nylon 6,6 is a very good compound for a lot of different uses. Nylon 6 is also good. It has increased elasticity and higher impact resistance, but it's not quite as common. For just a short history, nylon was first discovered and patented in 1935 by Wallace Hume Carruthers. He was an organic chemist involved in research at the DuPont facility in Delaware. He was attempting to find a synthetic fiber that could replace silk because it was actually in around World War II times, and they were short on natural materials. So they needed more synthetic materials, and it was first used to make bristles for toothbrushes, and then it started to replace silk and rubber in military items. So for nylon's impact on society, there are a lot of different uses, as I said before. It's found in a lot of clothing items, consumer products, carpeting, musical instrument strings, and 3D printed models. It can be used in rope or thread. In its solid form, it's used to make machine screws, gears, and machinery components that were previously cast in metal. It can be a substitute for low-strength metals, and a lot of times it's actually the plastic of choice for components in engine compartment of vehicles because the strength of nylon, the temperature resilience, and chemical compatibility all just works with those conditions. And a certain grade of nylon can be used in engineering for casting, extrusion, and injection molding. So a lot of different good uses there. I have a few examples here. In the top left corner, we see an example of the synthetic fibers just on their own. A guitar with nylon strings, jacket and pants. The blue picture you see there is actually a parachute made out of nylon material, a screw made out of nylon, carpeting, and rope, as I said. The economic effect of nylon is largely in Northeast Asia, actually. That's where they produce most of the nylon fiber in the world, and it's largely for textiles, but also other purposes. The global market for nylon fibers is still growing. It's expected to grow about 4% annually for the next 3 years and probably more after that. And nylon production is more expensive than polyester, so it is a higher price for the consumer in terms of just synthetic materials, but it's still cheaper than cotton, which is a natural material. So now we are going to go over the chemistry of nylon synthesis. Here's the overall chemical reaction. There's adipic acid as one monomer and then hexamethylene diamine as the other, and they come together to form nylon 6,6. If you'll notice, adipic acid is a dicarboxylic acid with a carboxylic acid on both ends, And then hexamethylene diamine is, like it says, a diamine. So there are two amine groups. So nylon can be made from step growth polymerization or condensation polymerization. In step growth polymerization, two monomers react to form a dimer, then a trimer, etc. until a polymer is formed. And in condensation polymerization, part of the monomer is actually kicked out as the polymer is formed, and we get byproducts. So that's what nylon 6,6 is. We get our nylons from diacids like adipic acid and diamines like hexamethylene diamine. The reactions do not require addition of a catalyst because there's an acid and it works well. And in the process of the reaction, a nylon salt is produced, and some intermediates are ammonium and an amide dimer. Now we are going to go over the mechanisms for this reaction. The first step we have is protonation, which a lot of us are used to with the acidic reactions. So we start with two adipic acid molecules. One's going to donate a proton to the carbonyl oxygen of the other, and that's how we get things started. When the oxygen is protonated, the carbonyl carbon becomes more vulnerable to attack by the nitrogen of our diamine. So the second animation there shows the amine attack. It attacks the carbonyl carbon, and an ammonium intermediate is created. On this slide, we show the oxygen stealing hydrogen from nitrogen, an amide dimer forming, H2O is expelled, and an acid catalyst is regenerated. So it says electron musical chairs on the slide because there are a lot of electrons moving a lot of different places, and ultimately we get that production of a dimer. So this slide shows that if you have a dimer and you add either an adipic acid or a hexamethylene diamine, you're then going to get a trimer. And if you keep doing this process, you'll eventually get a polymer. Information about the thermodynamics of this reaction was not super easy to find. However, polymerization is a lot of times exothermic, so it's a release of energy and considered energetically favorable, which means the reactants have a higher quantity of energy than the products, and this reaction doesn't need a catalyst, so at a high temperature we can assume that it's going to proceed. And there's also increasing entropy, which is the randomness or disorder of the system. We can see that with elevated temperatures and the byproducts that are produced from the molecules that act as the reactants throughout the process. The equilibrium of this reaction does have to be taken care of with a vacuum because otherwise it would reverse according to Le Chatelier's principle. A diacidic reaction produces water molecules as a byproduct, and then diamine reactions produce hydrochloric acid as a byproduct. So these two things need to be taken out in order for the reaction to proceed how we want it to. Okay, now it's time for the engineering of the large-scale synthesis of nylon. In this process, equivalent amounts of hexamethylene diamine and adipic acid are combined with water in a reactor. They are crystallized to make a nylon salt. The nylon salt then enters a reaction vessel where polymerization takes place and molten nylon 6,6 is formed, which can then be granulated or directly spun into fibers depending on what it's going to be used for. Here is a diagram of the synthesis process. We see water, hexamethylene diamine, and adipic acid going in. They're making a nylon salt. There is an evaporator because remember we want to get that water away. You want to get it down to its purest form. And then the polymerization reaction takes place, and it's either going to be made into flakes or it goes to the spinneret where it can be made into long thread-like fibers. And here's another image. I think it just shows the process a little bit more clearly. So we have, again, the two different monomers going into the same reaction vessel. The water is leaving so that we can make sure the reaction proceeds in the right direction. And it shows after that things are being added to make sure that we get the final product that we want in the form that we want. So if we want fibers, if we want pellets, etc. The chemicals involved in nylon synthesis can be harmful to humans in a few different ways. So the personnel who are transferring the chemicals into their reaction vessels must be wearing proper protective equipment. And to go along with that, there are different regulations about combustion protocol, water guidelines as far as the waste, and also air standards. Actually, nitrous oxide is a greenhouse gas that can be released from the production of nylon 6,6, and that's a contribution to global warming. So there are definitely standards for all man-made synthetic fibers, but especially nylon, that must be followed. For quality control, there are a lot of different qualities that can be tested in order to ensure that the compound that you are getting, the polymer that you're producing, is what you are expecting and what you want. So different things like melt index, flexural properties, color testing, moisture content, coefficient of friction, and the list goes on. Usually there are specific pieces of equipment that producers will have to test all of these things. And for environmental issues, unfortunately, there is quite a bit of pollution that can be associated with nylon. Like I said, the release of nitrous oxide in the actual production, and 3 times more energy intensive than cotton to produce. So it is a quite energy intensive process. And there's also water pollution whenever they're trying to color it, dye it, and also microplastic pollution. So this isn't as much to do with the production of, the synthesis of nylon itself. However, nylon doesn't, break down, so it can contribute to the ocean pollution, especially nylon fishing nets, which is really unfortunate. Here are my references, and lastly, I just wanted to say thank you for listening to my presentation. I hope you are doing well amidst all of the unknown and crazy circumstances.